This video is about simple continued fractions for square roots. In particular, it is about their periods. We'll quickly review the periodic pattern that appears when a square root is expanded into a simple continued fraction, and then we'll show some plots to see how the period tends to vary with the number whose square root we expanded. Let's get started. Generically, here's what the pattern looks like. We can represent the square root of x as a simple continued fraction. a0, a1, a2, and it continues on to some a sub n minus 1 and ends with a sub n. The first term, a0, is non-repeating, but the rest repeats. Within the repeating part, all the terms up to but not including the last one form a palindrome, and the last term is 2 times a0. Let's also review what we mean by period. The period is the number of terms in the repeating part. For square roots, the period will always be the length of the palindrome plus 1. In another video, we discussed all of this in more detail, and we looked at a table like this. The table has x in the first column and the expansion of the square root of x in the next two columns. This column has a0, the single non-repeating term, and this column has the repeating part. The last column has the period. As we just mentioned, the period is the number of terms in the repeating part. In that video, we explained that as x increases, we can find longer palindromes. The length of the palindrome and the period differ by 1, so we can also say we find longer and longer periods. The smaller numbers have short periods, but as x goes up, the periods can be longer and longer. You can look at this column and see that longer periods appear as x increases. When x equals 94, the period is 16. It's the longest period for any x less than 100. A viewer made this comment about that video. The value of a0 seems to be somewhat correlated to the length of the palindrome. I wonder what they would look like plotted against each other as a0 goes to infinity. Thanks for that comment, Davey Nov. Let's look at some plots. We'll start with one that goes up to x equals 100, similar to the table we just saw. The horizontal axis has x, and the vertical axis has the period of the expansion of the square root of x. As x increases, we continue to see some short periods, but we see longer and longer ones. This point corresponds to x equals 94, which has the longest period, out of numbers up to 100. If we draw a smooth line over the maximum periods, it seems to take this kind of shape. Mathematicians have found equations that bound the period. We'll overlay one of these equations on this plot. The line represents 0.72 times the square root of x times the natural log of x. 3 points exceed this, but the curve bounds the period for any x greater than 7. It isn't so easy to see here, but square root times natural log has a similar shape as what I just drew by hand. Here's another plot. It has a0 on the horizontal axis and the maximum period on the vertical axis. Let's take a little time to make sure you understand this. These two red lines are at x equals 49 and 64, which are consecutive perfect squares. The square root of any x between these two lines will be 7 point something, so a0 will be 7. The longest period between the two lines shows up on the lower plot. Look at these 2 points. When x is between 49 and 64, a0 is 7 and the maximum period is 11, which appears on the lower plot. Stop the video if necessary to make sure you follow this. We'll add lines for the remaining perfect squares. Here a0 will be 8 and here it will be 9. If we go to the left, they decrease all the way to 1. What we did to create the lower plot is find the maximum value between adjacent lines and plot it against a0. Stop the video and make sure you understand this. We'd expect the maximum periods to go up as a0 increases, and that is the trend. But something that we might not expect is it's kind of noisy. The maximum doesn't go up steadily and even goes down between a0 equals 6 and 7. Do you see anything else interesting? Let's extend the plots to larger values of x and a0. These go up to x equals 10,000 and a0 equals 100. We still see that there are short periods. In fact, we can make a stronger statement. No matter how large we make x, we'll continue to see small periods, but we continue to see longer and longer ones too. This is the largest period for any x up to 10,000. When x equals 9,949, the period is 217. Now that we have more values compressed into the plot, the shape of the maximums gets clearer at the lower end. We can see what looks like a pretty sharp boundary, but in the lower plot, we see the maximum period against a0 continues to be noisy. Let's go up to x equals 1 million and a0 equals 1,000. Of course, there are still short periods, there always will be, but we keep seeing longer and longer ones. This is the longest one. When x equals 969,406, the period is 2,664. I'll overlay that bounding equation on this plot. Up to x equals 1 million, The curve still exceeds the periods by what looks like a lot. Maybe this would close up some if we went to much higher values of x, but the period will never exceed it. I'm doing this on a laptop, so going more orders of magnitude would be challenging. But what we saw so far gives a glimpse of what this looks like if we go up to a number that is pretty large at least. I hope you found it interesting. In this video, we reviewed the repeating pattern that appears in the expansions of square roots and looked at the period as x increases. That's all for now.